Thank you, Jose Pablo. Thank you, Fernando. Thank you for having us. I am Jean-Louis Repetto. I am the commercial manager for Ampacity, and I live and work in France. I'm going to take you through the first steps of this presentation, and then Rena will take over. So first, the physics of dynamic line rating. How does it work? Dynamic line rating is about operating an overhead line as close as possible to the thermal limits without compromising safety, and of course without damaging your equipment. So to consider the thermal limits, you have to consider two things. First, the maximum conductor temperature itself. It's a given feature of the cable given by the cable manufacturer and confirmed by the line designers. They will state you have a maximum operation temperature that is maybe 70 degrees, 72 degrees, 75, 80 degrees, and the dispatch engineers must not cross this limit. Secondly, you have to follow the minimum clearance rules, also designed by the lines designers. So they will say you have a minimum clearance in all the spans of your line, and it amounts to not crossing a maximum sag limit. That is also part of the design. So if you operate your line the classic way, you will take care of these two limitations, and you will operate with static ratings. In France, for example, we have seasonal ratings. They are fixed but seasonal. We have winter, summer, and interseason. These ratings are based on the worst possible environmental conditions. That is, you take into account the fact that there will be no wind, that the ambient temperature will be maximum possible, and there will be no cloud at 12 noon. So these are the worst possible conditions that define your static seasonal ratings. Of course, you know that these conditions are just for safety, and that most of the time there are better than that. You have a little wind or some clouds, or the temperature has dropped a little. So all the principles of dynamic line ratings are based on knowing conditions and using the available margins safely. To do that, you have to monitor the line, its condition in real time. So if you know sag that you see on this diagram above, if you know sag in real time, you will know the margin that you have before you reach maximum sag in meters, and you can convert this margin into amperes and know what is the gains that you have that are available before you reach your safety limits. I'd like to say that it's very simple, and it's quite nice, and thank you for listening, but it's not so simple. In fact, if you see here on the right on this drawing, it's a CIGRE drawing, and you see that the conductor is in a thermal equilibrium affected by solar radiation, obviously, ambient temperature, the line's load, conductor going through the load going through the conductor, and cooling by wind. And since we are not in a lab, this thermal equilibrium is always changing. So you have to take into account these changing parameters if you want to do dynamic line ratings. In more details, I said you have thermal irradiation, so it's always there during the day at least, and it will affect the ratings, but not very massively, not very significantly. As well as ambient temperature, it changes, it goes up and down, and it will also affect the ratings. This is why we have in some countries winter ratings and summer ratings. So all this is true. Nevertheless, the most important parameter is wind, because this is the massive cooling effect that will give you more or less gains. If you look at the diagram to the left, it's an IEEE chart. So these are the official charts for a certain type of conductor. It's not important. What's important is the shape of the curves. And as you can see at the left, you have the reference curve showing for which load the maximum conductor temperature is reached. So on this diagram, we see that around 1000 amps maximum conductor temperature, which here is set at 75 degrees, is reached. Now, this is for the design of the lines when there is no wind, or in Europe, 0.5 meters per second. Now, if you have 2 meters per second, you can see that the gains are dramatically impressive, because the capacity of the same conductor has doubled, only with 2 meters per second of wind. Sorry, it has increased by 50%. I'm going too fast. Now, with 5 meters per second, in that case, the capacity of the conductor has doubled without any further action of any sort. So this is attractive enough to think about developing methods to do dynamic line rating. So as I said, it is not very simple, because to find the answer, what is my margin, this answer cannot be found by solving one simple equation. That's why international bodies like IEEE and CIGRE have designed standards that are applicable if you want to engage in dynamic line rating. So there are different types of standards. The most important to remember, if you want one, is the IEEE 738 here on the left, which is what we call the thermal model. There is also a CIGRE thermal model. They are relatively similar. Anyway, if you have all your the data available, you need to run them through this thermal model to get usable information to perform dynamic line rating. So for those who are interested, here we have listed all these standards, and the CIGRE ones can be downloaded for free on the CIGRE website, and the IEEE is you need a subscription, you need to pay. If we summarize, to do dynamic line rating, you have at the center the thermal model, and you have to feed this model with parameters like clearance or sag in real time. That is paramount to conductor temperature, of course. Sag is the ultimate consequence of the conductor temperature at a certain moment. You need your design properties to be able to know where your limits are, to make calculations on the gains, on the available gains. You will need the line's load to compute the gains, and also for other applications like transient ratings. And you need the weather parameters, that is wind speed, ambient temperature, and solar radiation. So all these are crunched into the thermal model, and the output will be Ampacity ratings, dynamic ratings, real-time ratings, maybe forecasts if you want to do that. That's the theoretical approach. In fact, there are two basic ways to do that. The one we favor at Ampacity is based on sensor. So you will have with a sensor mounted on the line measurements of effective wind, sag, current. Conductor temperature is derived from the sag with the state equation of the conductor. And in addition to these field measured parameters, you need ambient temperature and solar radiations. These are relatively easy to collect, especially nowadays in the 21st century. They are weather web services, so it's simple to subscribe to a web service provider and get the information with granularity that is needed to perform the computations. So again, with the thermal model and some computing power, you get your ratings. The other method that has been also developed for a couple of years, a number of years rather, is based purely on modeling. All the parameters, temperature, wind speed, and solar radiation are collected from also weather services and computed to perform thermal modeling. As you may have understood, we do not favor this approach. Comparing the available method from left to right, so you have the sensor-based method with line-mounted sensors measuring sag, which is our method. The nice thing about it is that the third-party inputs that you see at the bottom of the box are only ambient temperature, solar radiation, and possibly line current, because the same sensor also measures the effective wind affecting the conductor. Another method is line-mounted clearance sensor. So instead of measuring sag, you measure clearance. So it's another method. And as compared with the first one, you also need to collect the effective wind from a third-party input. Third method with temperature conductor temperature sensor mounted somewhere on the conductor. We do not favor this approach because conductor temperature is very difficult to measure. It can change along the line, even along the same span if there are some obstacles blocking wind. And the probe itself, being in a box, will act as a radiator, a heat sink, and the sensor itself, the probe, will affect measurements. So we do not favor this approach. And lastly, the weather model-based approach with no sensors at all on the line, on the conductor, only weather stations and weather modeling. In terms of the features, we have drawn this table to compare these four approaches. This is based on experience. The first questions that we have from our customers are, do we need a survey to know how to install the sensors? So does it take some preparation work to do that? Is it easy to install? Is it long? Do we need an outage, shutdown, rather? Is it complex? Do we need to train people to do the installation? Do we need to calibrate the sensors? What about the power supply? So all the practical implementation aspects are important features that you have to consider if and when you start a dynamic line rating program. After that, you have to be conscious of what you can get in terms of measurements, data, field data. Again, I repeat, the most important after the line condition itself, sag or clearance, is the wind speed. And after that, to have good quality outputs, you need a certain amount of processing power, and of course you need to be able to check your measurements, your results against maybe field checks or comparisons. So this table is a bit complex to read, but as Fernando said, the presentation and the recordings will be available after the webinar. Now, does DLR apply to all situations everywhere? Almost. Firstly, the dynamic line rating is for overhead lines, obviously, but you may want to perform the same, to have the same approach to underground circuits or the underground part of a hybrid circuit. So there are methods to do thermal rating for underground cables. Obviously, it's not based on the same sensors or on the same measuring method. However, there are standards and algorithms that are used to perform the computations. Of course, the gains that you can get underground are not as spectacular as the ones you can get with overhead lines, because there is no wind to cool down the lines, and the changes in the soil are not so fast as in the air. But gains are possible, and it's always good to monitor your circuits, if only for safety. After the circuit, the overhead line and underground circuit, there are transformers, so there are also dynamic ratings for transformers. It's not today's subject. So if we go back to overhead lines, in terms of voltage levels, DLR applications can be done from 20 kV to 800 kV. We have all sorts of cases. The sensors can be installed with or without shutdown. It's important for EHV voltage levels, 800, 400 kV, 380, 220 kV. We have cases, especially in Europe, where installation is done live. DC circuits have not seen any dynamic line rating so far, because the sensors are powered by induction, and these lines, DC circuits, are only for EHV. So live installation is quite expensive, and so would be the installation to change the batteries or to do some actions on the sensor. So for the moment, there is no DLR on DC lines. You can do DLR with HTLS, high temperature, low sag conductors, if only to check that the sag is really as low as the manufacturer will say. Alloy type is not important. We have cases with AAAC, ACSR, even copper. It can happen. It's only a parameter, just like conductor diameter. The fact that the circuit is with dual conductors or triple, quad, whatever. Then results can be a bit disappointing if the conductor temperature ratings are low. So if you want to operate your line here, we put 40 degrees at a maximum 40, 45, 50 degrees. Of course, this temperature will be reached very quick. On a hot day, even without load, it can be reached. So don't expect exciting results if you want to do dynamic line rating with very low maximum conductor temperature. Now that can be discussed. Sometimes we have seen that some utilities are a bit too conservative about that, but it's their choice. In terms of accessories like spacers or dampers, the DLR is not affected by these accessories. And it does not affect them as well. The sensors are put a bit away from spacers or dampers, and let's say there is no interaction between them. Finally, all sorts of circuits can be equipped. Rena will explain you a few application examples. As for us, we have seen circuits from 2 to 100 kilometers, some in the plain, some in the mountains, some in straight lines, some with many turns. So it really depends, and every case is different. Rena now will take over and give you a few examples of application cases, real cases.
Okay, thank you very much, Jean-Louis. My name is Rena Kuwahata. I'm the Business Development Manager at Ampacity. I'd like to continue the training session now to the second module on applications, examples of implementation by grid operators. Grid operators exist in various forms of company structures around the world. In Europe, there are transmission and distribution system operators who own, maintain, and operate the grid assets like power lines and substations. They also have the mandate to ensure that there is sufficient generation to meet demand at all times, even if they may not actually own the generation or retail businesses themselves. The core mandate of a system or a grid operator is to ensure the security of the grid at all times, so there are no damage to the grid assets, and to design and secure sufficient grid capacity for reliability so that the cause of a power outage to customers is not caused by insufficient capacity to transport energy from the power plants to the consumers. And also to aim for a lean design and maximum utilization that results in delivery of affordable electricity supply. This means to make sure there is sufficient grid capacity to access cheaper sources of energy. These are universal mandates for all grid operators. For specific regions, there may be additional mandates like ensuring transition to carbon-free energy sources. To achieve these core mandates, the grid operator has an intricate chain of activities which are carried out on a rolling basis. This is what I show here. It starts from long-term planning, years or even decades ahead, based on future scenario projections to decide which power lines and substations need to be upgraded, replaced, or new ones created. Once the assets are built, they need to be maintained in tip-top condition so that they are available when they're needed. Therefore, the next activity is asset management and maintenance planning, which starts years to months ahead. Then to make sure we have enough grid capacity tomorrow to deliver the expected amount of energy, the grid operation planning process starts a week to a few days ahead. In these days, before real time, power flow calculations are performed using grid models that reflect what is expected to actually be the status on that day in terms of the grid, including scheduled maintenance outages, renewables in feed based on weather forecasts, power plant production schedules, expected power consumption, and cross-border trade. If the power flow simulation indicates that an overload of a power line is expected as a result, the grid operators take action to remedy the situation. Finally, if the grid operators did their job right, we will continue to have a good quality electricity supply for our daily conveniences. If the grid operator has developed such an intricate plan over decades, perfected the art of how to deliver reliable, good quality supply, why would they need dynamic line rating? The answer is that there are major changes taking place. Decarbonization of the power supply, decentralization of power supply and proliferation of electric transportation, digitization of power systems, monitoring and control, regulatory changes like unbundling and incentive regimes, and climate change, causing necessity to rethink scenarios, forecasts, risk management, resiliency and robustness of systems, and also the power flow management methods. What is the value that dynamic line rating provides in facing these challenges? It's quite simple if you think of it in terms of the value of having more grid capacity and having more visibility or situational awareness through monitoring. The value of extra grid capacity is well known. You can avoid or delay grid reinforcements that may be necessary to integrate renewables. You can cater for peak loads, for example, caused by electric vehicle charging, ease grid congestions and avoid having to use expensive or disruptive remedy actions, which I will explain more later. You can increase trade capacity with neighbors with cheaper power prices. This means you can also sell more to your neighbor. Facilitating broader access to cheaper energy means generating social welfare. The main benefit of having more visibility and situational awareness through monitoring with DLR systems is that you can evaluate better your asset performance and risks, which can be applied in asset management. going to skip a little bit, come back to this later. The main value of dynamic line rating to grid operators is related to congestion management. It gives flexibility to avoid otherwise cumbersome and costly remedial actions. In Europe, a number of congestion management actions are recommended by the Association of Transmission System Operators, called ENSO-E. That's what you see here. Some of them are considered cost-free, like modification of grid topology and reactive power control, while some of the others may incur costs, like redispatch and renewable curtailment. By having additional grid capacity enabled through dynamic line rating, we can avoid a lot of these actions by just having accurate information at the right time. For this, forecast dynamic line rating plays a critical role. Dynamic line rating systems without accurate forecasts do not provide as much value as those with good forecast algorithms. For example, 1 hour ahead of real time, the state estimator in the Grid Control Center automatically calculates the N-1 security power flows to assess on a rolling basis the expected loading on the line. For this calculation, 1 hour dynamic line rating forecast values from our systems are automatically streamed into the calculation module. In a similar way, 4 hour ahead, a day ahead dynamic line rating forecast values are used for grid security calculations instead of static ratings. By using the DLR values directly in the N-1 security calculations, the expected congestion or overload risks are automatically reduced. Automating this process means that it reduces human errors of handling the data. It also reduces the need to even consider cumbersome topology actions and costly remedial actions. All of this must be in a good quality, though, so that it guarantees no violation of safety limits like minimum clearance and conductor temperature. Now, I'm going to describe an example of how dynamic line rating is actually used by a transmission system operator. This is typically how you would see the output in a control room. This is a screenshot of a monitor in the National Grid Control Center in Belgium. The example shown here is a result of what happened after market close on 13th of September 2017. The blue line is the static seasonal rating, while the red curve is the dynamic line rating coming from the Ampacity sensors. The green curve shows the power flow on a major 380 kV line in Belgium. So, on the 13th of September, the Grid Operations Center was facing a challenging outlook for the next day. Energy exchange between Germany and France, which inevitably flows through Belgium, was settled on the day-ahead market, so they were expecting high north-to-south flows on the backbone transmission network, especially in the evening peak hours when demand picks up, and when Germany had plenty of wind energy to export. However, one of the backbone transmission lines was out of service due to maintenance work. It was being upgraded to a line with high capacity, so it couldn't be brought back into service at short notice. At this stage, this meant that during those peak hours, it was highly likely that the resulting power flows would be too high to ensure an N-1 security of the grid. Therefore, the operators in the Grid Control Center prepared to change the transformer tapping at the phase-shifting transformers positioned at the borders of Belgium with Netherlands to redirect the power flow away from the congested areas. The maximum tap setting for the PST is 18, but for day-ahead operation, typically it is limited to a maximum of 6, and this is to leave room for emergency situations in the intraday. So that means the PST tapping was prepared to be at its maximum possible setting for the day ahead. However, they realized that this would not be enough to get rid of the potential N-1 security violation. Therefore, they decided to make some topological arrangements in the 150 kV subtransmission grid, also to try to redirect away some of the power flows. Even with all the effort by the grid operator to solve the congestion using his own assets, it could not get rid of the potential N-1 security threat. So at this point, they prepared to instruct some power plants to redispatch. This means instructing power plants in France to divert from the production schedule and increase their output, while at the same time instructing power plants in the Netherlands to decrease their output. Belgium is limited in terms of power plants in its own territory, especially to counter the expected large north-to-south power flows. There's quite some noise. Somebody might need to mute themselves. So they were prepared for the 14th of September, and then the clock ticked over to the next day. As the intraday activity started on the 14th of September, updates to the forecast consumption to the power plant production schedule considered. Also, considering also the intraday trading results started to roll in. Earlier then swiftly updated the expected power flow calculations for the critical evening peak, and the result was still quite tight, but manageable. The topological measures set in place the day before stayed as it was, but the phase shifting transformers didn't have to be tapped as high as anticipated. The tapping was set to 4 instead of 6. The resulting power flow is shown in the figure as the green curve. This is the actual line loading on the 380 kV transmission line. You can see the green curve becomes very close to the static rating, blue curve, in the critical evening peak hours. If the N-1 security calculations had been based on static ratings, this flow for sure would have resulted in security violation, causing the need to tap the PSTs for 6 or even higher, and definitely to activate the redispatch instruction of the foreign power plant. However, since Elia knew with sufficient confidence that in fact, in reality, there would be sufficient line capacity to buy reliable DLR, the grid would be N-1 safe without any action. This is because Elia is confident in the fact that dynamic line rating is a reliable limit to replace the static rating in N-1 security calculation. Therefore, for this particular case described for the 14th of September, dynamic line rating was able to save Elia expensive redispatching actions and also the need to tap further the PSTs. The next 2 slides I'll go through quickly because of time constraints, but please feel free to ask questions on them at the end of this webinar and even afterwards by email. So, if there are so many obvious benefits to dynamic line rating, why is it not more widely used? Actually, many grid operators already apply some form of flexible rating of their power lines and substations. It might be that they use ratings that vary between seasons, like winter rating and summer rating, like Jean-Louis explained before, or by ambient temperature, what is called an ambient adjusted rating. But these methods still underestimate a lot the additional capacity that actually exists. What is the bottleneck then to deploy real dynamic line rating systems, like the ones supplied by Ampacity? Based on our more than 10 years of experience, we can say that the major hurdles to adoption of these systems are not about the maturity of the technology or the reliability of the sensor systems. It's more about the way the incentives are set up for grid operators to really become active about driving down operational expenditure. So this can be in the form of a regulatory bottleneck, slow pace of coordinated decision making, and the methods used by and options available to grid operators to avoid potential overloads. If you manage to overcome the hurdles that I mentioned, then dynamic line rating can deliver significant benefits in the form of additional grid capacity and enhanced visibility. With enhanced visibility, you can monitor better the asset risks like temperature and sag of a power line. Forecast values for these parameters can also be provided together with the forecast dynamic line rating. And if you use Ampacity sensors that measure vibration, you can also detect physical anomalies like tower fall, galloping of the line, and icing on the line. With enhanced visibility, maintenance outages can be better managed by handling the power flows that need to be rerouted. This was done, for example, by the Dutch TSO. As an advanced user of dynamic line rating systems, you can start using data science and combining it with big data, artificial intelligence, etc., to make your existing processes and methods smarter and trigger automated responses. For example, the Belgian TSO has begun to adapt its power line maintenance strategy to consider more accurate line loading statistics and its impact on aging to inform its replacement plans. Also, we are in discussions with some utilities about linking the dynamic line rating to automated relay activations to enable active network management. Now I'm going to hand the ball back to Jean-Louis quickly for the next 2 slides.
All right. Can you hear me?
Yeah.
Okay. Yes, this is a screen capture of Elia's National Control Center energy management tool. So we can see on this screenshot, firstly, very kindly, they put our name at the top left of the screen. So our name is there because they use our data that are mapped into their EMS SCADA. To summarize this quickly, the Ampacity server is seen as an RTU by the front end computers of the SCADA system, and we provide standard frames. Here it's ICCP frames, but it could be IEC 104 or DNP3, IEC 101, or whatever, as long as they follow an international standard. And so these frames contain the data that are computed or measured by our sensors and our algorithms. So you see the transmission lines of ELIA are shown here by voltage level. It's not very clear, but you see on the top left 150 kV, and then below 70 kV, and on the right 380 kV and 220 kV. So these lines are here in blue. It's the line identifiers, and the load is shown next to the line identifier in MVA. So you have 22.8 MVA, 10.6 MVA, etc. And the seasonal limit is also shown next to it in MVA, and framed in yellow. You have the dynamic line rating limit as it is computed by our system. It's not the real-time rating that you see here, it's the 1 hour forecast capped. So let me explain. When you do dynamic line rating, you have the real-time rating that gives you the load that you can put through your circuit immediately at the same minutes where you are reading the screen. It's the available capacity of the line at this minute. Then with some more computations and algorithms, you can perform some forecasts. So we have forecasts to 30 minutes, 1 hour, 2 hours, 6 hours, or day ahead with 24, 48 hours or more. Now here we have the 1 hour forecast, and you can see that it is capped because ELIA decided to cap all gains at 30%. That is, even if there are more capacity available, ELIA will not consider capacity gains above 30%, which is good enough, if you ask me, for a transmission line. If you convert these MVAs into billable power, it's a huge amount. Anyway, you can see these available ratings for the next hour to the right. And as Rena said, these numbers can be used for the power flow simulations and the computations of scenarios for N-1 or N-2 contingencies. What else? Well, there are other screens that could have been captured with the real-time ratings, with the day-ahead forecast. What is important to stress now is that, of course, the ultimate destination of a DLR solution is to be used in real time with forecast or not, but I mean on a day-to-day basis in the work routine of the dispatch engineers in the control rooms. So firstly, they have to be confident in the ratings that you give them. And secondly, in terms of integration, the solution has to be integrated. That is, the data have to be mapped into the SCADA system, whatever it is. And you can apply different options with redundancy, with backups, historical data analysis, statistics. You can do a lot of things with the data. But firstly, the dispatch engineers have to trust the solutions. We have found in 10 years and more of existence that as long as the dispatch engineers don't trust you, you're not going anywhere. I have a next slide, I think, with animation. Fernando. Yes, so here we created an animation with real data that are from a real case. So I'm not going to disclose which case, but it doesn't matter. It's based on real data that we have that we replay with this animation. So at the bottom, the light blue curve is the ambient adjusted rating, what we call the ambient adjusted rating. So you can clearly see it's based on temperature, basically. So clearly you can see the 12 noon peaks. So when the temperature is maximum and the sky may be blue with maximum solar radiation. And the pink and blue curves are the blue curve is the dynamic line rating that our system provided, and the pink band is the forecast that we computed with our system. So if I stop the animation here, you see so the light blue curve is let's say a reference. Normally the ratings cannot be below that, and the pink band is one hour or well, it's more than 1 hour. Maybe it's 24 hours ahead. Sorry, and so
you can
yes,
yeah, you can use this pointer. If you want to
explain. Thank you. Yes, okay, perfect. I have it. So here is the band that show you the ratings available 24 hours ahead, and you can see that this band has some breadth. So we say it's derived from the confidence index that is required by the TSO or the DSO. Of course, all this is done on modeling and forecasts, and so you can request a very aggressive confidence index. That is, you want to be sure at 99.9% that the forecast is good, and in that case, it will be a little more conservative, and the band will be wider. So here, I don't know, maybe the confidence index was 95 or 98%. And what is important to see is that the rating that we give, that we provide, is within this band, and it has the same profile as the band itself. So it's a good sign as to its effectiveness. And it stays inside the band to follow the requirements of the customer. So in short, it's a forecast that you can use. You see here we had a slight wayward way. So that's the risk that you take if you choose a confidence index that is above 90%. You have some risk. What else? Our method is based on bilinear regression. So it's a bit like the linear regression that we did at school, but more complex, of course. And it's effective to do what we want to do because it shows not a maximum value, but a band of likely results. And then again, based on the confidence index that you agree to have, the forecast will stay inside that band. So you can use it. You can use it for various applications. It can be for day-to-day operation, or it can be for, in this case, if we have a day-ahead forecast, it's more applicable to energy market operations and day-ahead capacity forecast, things like this. Yeah, I think it's clear enough. Rena, if you want to continue.
Yes. Only thing to add here, just to make sure everybody is on the same page, that the vertical axis, which says perpendicular wind speed, that's actually in the video wrong. That's obviously should be the line rating in amps. And also the forecasting method, right? The linear regression that you mentioned is for the short-term forecast. The day-ahead forecast and the 2-day-ahead forecast also takes into consideration weather forecast information. And has a learning algorithm.
Okay.
To, improve over time. Okay, very good, thank you. And I continue to the slide again. How do we go back? So now I'd like to continue to the third part of the training session. We described already the benefits of dynamic line rating to a grid operator or owner in general terms, but I'd like to give some concrete examples from actual projects. We're a bit pressed for time, so I'm going to only explain in detail 2 of the 4 examples in this webinar today, but please feel free to ask any questions at the end of this webinar and even afterwards by email. I will be happy to explain further on the other examples as well. The first example is the benefit of increasing cross-border trade. In Belgium, all cross-border lines to its neighbours, namely Netherlands, France and Luxembourg, are equipped with dynamic line rating systems. Also, most of the internal 380 kV grid is monitored with our system. On the 19th of February 2015, the 2-day ahead forecast showed that the demand would be high due to typical winter temperatures around 0 degrees Celsius, and also the local supply was tight because of nuclear power plant outages. This meant that there was a high reliance on importing neighbours' cheaper supply. The 2-day ahead dynamic line rating forecast showed, so on the 17th of February, that the weather conditions would be cooling the critical transmission lines. This meant that 3% capacity increase could be relied upon the critical bottleneck lines inside of Belgium. This resulted in that the cross-border import capacity could be increased as well, so that 22% more energy could be imported during 4 hours compared to the case where the import capacity is calculated based on static ratings. This meant that Belgium was able to import cheaper energy in critical high price periods and were able to save close to 250,000 euros in supplying energy to its local citizens. So that's the first one. Unfortunately, I have to skip the example on wind integration due to lack of time. But wind integration is the obvious use case for dynamic line rating because when there is wind, there is cooling, and therefore there is capacity. For example, we are in a framework agreement with RTE France to deploy dynamic line rating systems at the moment, and this is mainly for wind integration. But for today, I unfortunately have to skip this. And we go to the third example, which is from Germany, where there are vast amounts of congestion on a daily basis. This is known to be mainly caused by increasing wind power installations in the north of the country, which needs to be delivered to the demand centers in the south of the country. This is compounded by the exiting nuclear and coal power plants, which are in the south, and they're being phased out at the moment. The German regulatory authority publishes annual statistics in which it reports the top congested lines in terms of numbers of hours congested, amounts of energy that needed to be redispatched because of the congestion, and the resulting costs, etc. For example, in 2017 and 2018, the annual costs of congestion management exceeded 1 billion euros each year. Using simple division, this is about 100,000 euros per hour or 4 million euros per day, which is costing German electricity consumers. Even if you look at only the redispatch component of the congestion management costs, I explained earlier that congestion management may include redispatch, counter-trading, demand response, renewables curtailment, etc. So even if you look at only the redispatch component, the cost is 23,000 euros per gigawatt hour. And we look at one example, this line Ville-Ost in West Germany, which is listed as one of the culprits for high congestions in the 2017 report by the regulator. On this line, we have our DLR system installed for 2 years. The summary of the performance is shown in this slide. This is typically how you would assess line performance of DLR. Here you see the duration curves of the dynamic line rating of the 380 kV line. Each curve is a summary of the 5-minutely data results over the 2-year period. On the vertical axis is the capacity gain given by the dynamic line rating as a percentage of the seasonal rating. On the horizontal axis is the percentage of time over the 2 years the dynamic line rating was at a certain value. This means that if you look at 50% on the horizontal axis, it gives the average dynamic line rating over the 2-year period, and you can see this is about 130%. At some point in time, over 200% gain was available, effectively doubling the nominal capacity. However, it would be unusual for a grid operator to actually load the power lines to twice the capacity because the capacity of the substation equipment connected to the power lines may not be able to cope with such high loadings. That means the bottleneck may not be the power line capacity. What is useful, however, is that there is more capacity than the static rating almost all of the time, specifically here 99.5% of the time. Also, 95% of the time, there's 6% above the static rating available, and 90% of the time, 14% above the static rating is extra capacity available. The question is, how does this help to reduce grid congestion? This line Bill Ost, as stated by the German regulators report, is often congested and causes the need to redispatch. The redispatch rule in Germany dictates that the most effective power plant to solve the congestion should be called to change its output, which are typically the power plants in close proximity to the congested line. In this case, there are a few power plants connected at the north end of the line, which are often subjected to downward redispatch. The redispatch information can be seen on the German grid transparency platform called Netztransparenz on the web. For example, let's take 14th of February 2017. The Neugas power plant at the north of the Ost line was instructed to reduce its output by 200 megawatts from 7 a.m. to 4 p.m. This totaled 1,750 megawatt hours of reduction in production in that day. What is the impact of this 200 megawatt power reduction on the line? This line is a 380 kV line, which means it can carry around 2,000 megawatts of power, considering the static rating. And without considering any losses between the power plant and the line, 200 megawatt reduction means there was a need to reduce the line loading by a maximum 10% of static line loading. Or in other words, 10% extra capacity of the line would have resolved the congestion and there wouldn't have been a need to instruct a redispatch. We know from the shown evaluated dynamic line rating performance that at least 14% gain is available for 90% of the time. To calculate the potentially avoided costs, we multiply the redispatch energy of 1,750 megawatt hours with the average redispatch cost of 23,000 euros per gigawatt hour, which is about 40,000 euros savings in one day. You can see for yourself from the data on the German grid transparency platform that this example is not an especially high congestion day, but a fairly typical day. So that's the two examples. I'm sorry to have to cut a lot of the material, but we are almost 3 o'clock, so I'd like to go to the end and show the customer testimonial.
My name is Philippe Carton. I'm the head of the National Control Center for ELIA, and ELIA is the transmission system operator in Belgium. Together with my team, I have to make sure that the high voltage grid is managed in a secure way. And what's also very important for ELIA, because it's part of our mission statement, is that we do everything in the interest of society. So that means that, for example, making efficient use of our infrastructure, it's part of our mission and one of our goals. There are two big use cases for ELIA using Ampacity. First one is in real time. Near the coast, we have a lot of wind farms connected, and without Ampacity before, if there is congestions, the only solution is to reduce or to curtail wind. In this case, once you install Ampacity, there is less redispatching you have to perform. And it's very interesting to see that there's a correlation between Ampacity and wind in feed. So the days when there's a lot of wind and higher congestion are also the days where there is more Ampacity given thanks to Ampacity. So this is the first very interesting use case which made our life easier, mainly at the coastal area in Belgium. And the second use case is that thanks to Ampacity, we can also provide more capacity to the day-ahead capacity calculation market. So there we talk about order of magnitude 5 to maximum 9% of additional Ampacity we can provide to the market coupling, which is very interesting for the market coupling because it will generate social welfare, again, in the interest of the society. So that's the second very interesting use case for Ampacity. What I really like about Ampacity technology, certainly if you compare it with other technologies, is that it actually measures the sag of the line. So it's very reliable, because other technologies might forecast or use algorithms taking into account weather, solar radiation, things like that. But it's always an estimation, it's an algorithm. Ampacity really measures the sag of the line, and it takes into account all parameters, even if you don't know it. So that's what I really like about technology. It's very reliable. You know there is a measurement device, and you know that you can trust on the measurement. That's very important for me. It's not just an algorithm, it's actually a physical device measuring the sag. If you look at the benefits for society or other market parties, it's clear that, for example, wind farms wanting to connect to the grid, they will get faster access to the grid if you make use of this kind of technology. I think it's a big benefit. Otherwise, they have to wait for investments, which takes very often 5 to 10 years' time. So they can get quicker access to the grid. This is important. But also for other market players, if you look at the added value it generates for the market coupling, this is social welfare. This is in benefit of all consumers and producers. They are able to sell or buy more energy under the international markets, of course under the condition that the Ampacity has forecasted additional capacity, but that's depending on the weather and things like that. So that's also very clear interest for society.
Okay, so now you can take forward the presentation, Karina and Jean-Louis. Thank you.
Thank you. I think Jean-Louis is going to continue the rest. Here we have.
Yeah, it's a wrap-up. Can you hear me?
Yeah.
Yeah. So we like to make the following point now. Dynamic line rating has become relatively common. It's a mature technology. It's been tried for more than 25 years, and our company has started research over 15 years ago and has started commercial deployments more than 10 years ago. So it's in terms of technology, it's mature, and you can see the proof of it just if you look at the tender round announcement of last year. You can see 1, 2, 3, 4, 6 of them in various parts of the world, Europe or the Americas, and more are coming. We know about that. So DLR is becoming commonplace. Of course, it's an innovation in certain cases, but if some of our listeners work for utilities, my message is be confident. It works well, and there are a lot of circuits equipped. As for us, we have 65 to 70 circuits equipped, so a lot of let's say experience about that. So that was my point. It's well proven up to the control room with the dispatch engineers, as you could see. The applications are obviously congestion management, interconnectors, and integration of renewable power. As Rena pointed out, we have a frame agreement with RTE in France, and most of the use cases will be for integration of wind power offshore or onshore. The nice point about DLR is, since we are in a smart grid forum, it's based on data and on measurements. So the value of the systems that we implement has nothing to do with the value of the assets that we monitor. It's the second order or third order amounts. So the return on investment is extremely quick. We have customers who do that kind of study. They assess the internal return rate, IRR, and it's really spectacular. So of course, if you really have to extend or reinforce your grid, ultimately you will have to do it, but that can be a little postponed, and we are talking about optimization and modernization when we are talking about DLR. So it's good in all cases. Now, after this webinar, I suggest that you go to the links here, and you have some readings to do, obviously, from ENSOE, from CIGRE, from us, possibly. You can get some training. We have a partner in Paris who is providing training on DLR. We also do, of course, in our factory and head office. If you're interested in the ELIA testimonial, you can go to the ELIA website and see how they explain their method, their approach to implement DLR. So that the first link to the right and below, you have their way to value the forecast that they use and the measurements that they use. And yeah, finally, the Ampacity DLR FAQ is can be a good read also. It will answer all the points that we forgot today. And finally, all the references, the papers, scientific papers, the standards, the CIGRE papers that were published over the years are listed here.